Hi, today we are going to talk about market models for interest rates. The HJM framework models the entire interest rate curve, but the modeled variable is the instantaneous forward, which makes some practical issues to rise. The first one is that the instantaneous forward is a variable which is not directly observed in the market. See that this is an abstract interest rate in the sense that no loan takes place on an infinitely small time span. The second one is that interest rate derivatives in general are not easy to price with a general AJM model. And the third one, which is connected to the second issue, is that provided that there are no formulas for pricing derivatives, also there is no obvious procedure for fitting the parameters of the model. These issues led to the creation of the so-called market models. The first of these market models is called the LIBOR market model. In this model, the underlying which is modeled is a set of forward rates with some tenor. This model has the advantage that both caps and floors have Black's formula available for its pricing. The second model is the swap market model. In this case, the variable which is modeled is the swap rate. And it also has the advantage of having Black's formula, but instead of for caps and floors, in this case it's for pricing swaptions. It has to be noted that these two models are not compatible with each other. This happens because the LIBOR market model assumes that the forward rates have some log-normal distribution, and the swap market model assumes that the swap rate has some log-normal distribution. These two facts cannot happen at the same time. The LIBOR market model was introduced in 1997 and is also known as the BGM model from the name of its authors. LIBOR rates with tenor delta are interest rates in simple compounding for the period going from capital T to capital T plus delta. The LIBOR market model considers the evolution of several forward rates with a common tenor. Each of these forward rates is modeled under a different probability measure. Afterwards, the evolution of all of the forward rates are rewritten in terms of a common T-forward measure. Interest rates in simple compounding are defined in terms of zero-coupon bonds in the following way. See that if we multiply both sides by the zero-coupon bond maturing at capital T plus delta, we arrive to the following expression. This expression is interesting because on the right-hand side we have two zero-coupon bonds. This means that we can replicate the LIBOR rate times the zero-coupon bond just by buying and selling zero-coupon bonds, which are tradable assets in the market. Therefore, the LIBOR rate times the zero-coupon bond is a tradable asset. And if we divide by some numeraire, what we get is a martingale under the appropriate probability measure. If we take the zero-coupon bond maturing at capital T plus delta as a numeraire, then we will see that the LIBOR rate is actually a martingale under the T plus delta forward measure. Assuming log-normal dynamics under the probability measure where the forward is a martingale gives rise to this diffusion, where this term over here is a Brownian motion under the T plus delta forward measure. In order to perform a change of measure, we can use the Radon-Nikodym derivative. Recall that the Radon-Nikodym derivative between two T forward measures is given by this quotient of zero coupon bonds. Now, see that if the LIBOR is some forward rate in simple compounding, we have the following relation between two zero coupon bonds. This leads to the following representation for the Radon-Nikodym derivatives between the T forward measure and the T minus delta forward measure in terms of the LIBOR rates. If we want to write a Brownian motion in the T minus delta forward measure in terms of the Brownian motion in the T forward measure, we will need to use Girsanov's theorem, which gives the following representation for the Brownian motions, where the process yt has to satisfy that the stochastic exponential of the process y has to be the Radon-Nikodym derivative between the change of the two measures. Using Ito's lemma, we can see that this process is given by the following expression, where this guy over here is the volatility of the LIBOR rate for maturity capital T. And finally, we have this relation between the Brownian motion in the T forward measure and the Brownian motion in the T minus delta forward measure in terms of the LIBOR rate and its volatility. We call that the model that we were considering does not model a unique LIBOR rate. Instead, it is modeling several forward rates which are consecutive. We can iterate the previous reasoning to rewrite some Brownian motion in terms of another Brownian motion in such a way that we can obtain relations between Brownian motions which are tenors away through this expression. Similarly, we can also obtain an expression for Brownian motions where the direction of the shift is positive instead of negative that we had obtained previously. Altogether, we have the following relation between Brownian motions. And also we have the following expressions for all the LIBOR rates in terms of a unique Brownian motion in the P forward measure. We now consider formulas for pricing caps and floors. In order to do so, consider a unique LIBOR rate whose diffusion is given by this expression. Consider a caplet at time t for the period going from capital T to capital T plus delta with some strike k. Its price is given by Black's formula, where this phi is the cumulative Gaussian distribution and d1 and d2 are given by this expression, which depends on the LIBOR rates and its volatility. We can obtain similar expression for a floatlet, and just by adding up several terms we can also price caps and floors. The swap market model was introduced by Jamshedian in 1997. This model models the swap rate as a log-normal diffusion. The derivation of the model and of the pricing formulas follows closely the use of the change of measure toolkit which was used in the LIBOR market model. Similarly, we also have Black's formula for pricing swaptions. Suppose that we have a greeting time denoted by Tj, which is spaced by some tenor delta which is greater than 0. The swap rate associated with this grid of dates is given by this expression. For some t between 0 and t0, we define some t0 martingale dt using this expression over here. Using this martingale, we can define the forward swap measure through its Radon-Nikodym derivative. It can be proven that under the swap measure, the swap rate is a martingale. This model assumes that the swap rate follows a log-normal distribution under the swap forward measure. The price of a swaption with strike K for a swap with reset and payment dates given by Tj is going to be given by Black's formula, where the terms d1 and d2 are going to be given by this expression.